Okay. So the paper we are going to discuss is side channel security of superscalar CPUs, which was published in Design and Automation Conference in 2018. I went to how many of you? Okay, I'm not going to ask. So why they wanted to present this paper? Because it is difficult to analyze vulnerability of a new device. So like if let's say a new CPU is released, let's say by Apple or by Intel. So how I know what kind of vulnerabilities it has? And provided that I don't know the internal architectural details of that CPU. So I don't know the internal architectural details, and I want to find out what are the sources of information leakage, architectural sources of information leakage within that chip. Okay. And the second thing is like, even let's say we have a chip and I know the internal details of that chip, and I know in advance what are the possible sources of information leakage. So I take that information into consideration when I'm writing the software for that particular chip, right? And now I develop a side channel resilient software or a library, but I develop it only for a particular chip, like it will work on a particular chip A. Now, when I want to move, let's say, the same library of software from chip A to the chip B, I want to run on the chip B, which has different architecture. There are no guarantees that there will be no software side channels, information leakage from this software running on a different CPU. Okay, so how can we like achieve this portability of side channel resilient softwares? Okay. Now, the technical problem of like achieving or addressing these two problems is like, so like the technical description of these two channels, which I already have explained, is because when you develop a side channel resilient software, you have previous knowledge that, okay, what is the architectural detail of this particular CPU? But when I move to the new CPU, I don't have those details. I cannot take them into consideration, right? So it will not be any more resilient, and whatever countermeasures I had, they will not be effective anymore on the new CPU. Okay, so the research problem is to analyze how microarchitecture features of a CPU, which can vary across devices, play a role in pinpointing the sources of the information leakage when we run the software primitives on top of that architecture. Okay, I'm skipping this because I want to focus more on today's slides. So how many of you, just tell me, how many of you knows what is superscalar CPU? Okay, superscalar CPU is one which can execute one instruction in one cycle, one clock cycle. Okay, superscalar CPU is one which can execute more than one instructions in one clock cycle. So definitely superscalar CPU is more performant as compared to the scalar one, right? And processes are normally pipeline, like modern processes are pipeline. I don't think there are any machine using non-pipeline processor anymore. So there are multiple stages of the pipeline. Like what happens is, what you can do is like, let's say you have this CPU, and what you can do is like, okay, I give you an instruction, and then you give me the output after executing this instruction, right? And let's say that when I execute this instruction, it takes 10 time units. To make it simple, let's say 10 seconds, right? And let's say the instruction execution starts only when the positive edge of the clock arrives. Okay. And then it continues, right? So these are 10 seconds, right? And then on the next clock cycle, the next execution of next instruction starts, right? But these 10 cycles are, let's say it is let's say I'm saying it is my add instruction. So add instruction is taking 10 seconds, which means that next instruction has to wait for 10 seconds before it can be executed, correct? Everyone with me? Now I want to speed up my execution. I don't want my subsequent instruction. Let's say this was add 1, this is add 2. I don't want my add 2 to wait for 10 seconds before we are having the background discussion because I was not able to have a lecture last day. So still. So what we can do is like, I don't want my add 2 instruction, second add 2 like wait for 10 seconds. So what we can do is like, I can pipeline my CPU, okay? In such a way that some part of the add operation or whatever operation is done, I can like divide it into 2 stages. So if in 2 stages, second instruction has to wait for 5 seconds, right? 5 time units. And if I divide it further, then the amount of time for which the subsequent instruction has to wait keeps reducing, ideally, okay? But that is not how things work practically, but I mean, this is what we want to achieve ideally, okay? Okay, so the stages we have like typically in a processor, they are like, you have fetch stage, you have decode, you have issue, you have execute or memory, and then write back. Okay, so it's clear from the name what we are doing. In fetch, we are fetching the instruction from the memory and putting it in some register. Then in decode, we try to unpack that instruction and find out what kind of operation that instruction wants to perform. In issue, so what we need to do is like, if let's say talk about superscalar processor. So let's say it is dual issue. So you have 2 instructions here. 2 instructions are fetched, 2 instructions are decoded. And then in issue stage, what we do is like, can we issue both of those instructions for the execution or not? It depends upon basically 2 things, whether these 2 instructions have dependencies or not. So one thing, dependency, and second is whether the functional units on which those instructions need to execute, let's say one of them is add and another is multiply. So whether the functional unit in the next stage, so this stage contains the functional units. So whether those functional units are available or not. So if there are no dependencies between 2 instructions which are decoded and the functional units they need, they are available. If those both conditions are met, we can issue them for the execution. Okay. So this is like, what is the job of the issue stage in the superscalar CPU? Any questions?
Yeah, dual issue means that it can execute two.
Sorry?
Dual issue means that it can execute 2 instructions at the same time?
Dual issue mean we can issue 2 instructions at the same time, but then in the paper they are, so here is the thing. So at the time when they wrote the paper, though at that time the ARM Cortex A7 was like released, but it was no information was given about the internal architecture of that. Like even if the information was available, it was limited. So for example, in one document, they listed that, yes, it is a dual issue, but it is partially dual issue. So partially dual issue mean that sometime, some of the instructions, some pairs of the instructions can be issued at the same time, but some other pairs of instructions, they cannot be. Why? This is like one of the questions which they wanted to answer in this paper by how to say, looking at CPI indexing of the micro benchmarks. Okay. So so I will explain what is CPI later. But here is like, this is the information they had available. But it doesn't give any how to say greater details about the architecture. So this is just a logical figure. You have fetch, decode, issue, but there is no information available. Like, yes, they said it is dual issue, but in what scenarios you can do the dual issue and what other scenarios you cannot. Second, like, yes, they show here like there are pipelines, but how many pipeline stages are there, they don't know, right? And whether that all the ALUs, the ALU they have, whether it can do the multiplication or not, and how many ALUs are there, right? So they wanted to find questions to all these answers to all these questions by looking at the CPI indexing of the instructions. But before I explain the CPI, what is CPI? So there are like some other terminologies which are explained mentioned in the paper. So I don't know whether you are aware of them or not. So I have explained what is meant by partial dual issue in context of this paper, but what is ISA? ISA is like actually stands for instruction set architecture. So it defines that, okay, what is the set of the instruction that is supposed to be executable on a given processor. So if I know that like this is the ISA for Intel, I have all the set of the instructions. But it is possible that the same ISA is implemented by using different architectures or different architectural implementation details. So here is an example. So for example, all these processors by Intel, they have the same x86 ISA, but all of them have their own differences how they implement the microarchitectural components. So basically what I'm trying to say is that there is decoupling between the ISA and the architecture which is implemented. There is flexibility. You can implement the same ISA in many different ways. Maybe one is optimized for performance, and other is maybe optimized for energy or power consumption. Okay. Pipeline buffers. How many of you know these pipeline buffers? Okay, so I talked about like these stages: fetch, decode, instruction, execute, memory, write back. So which basically mean like something is a data, let's say that something is data signals. They need to flow from one stage to the next stage, right? And what is the purpose of having this? I mean, why we even want to have this multi-stage pipeline in first place? Because we want to have our different instructions into different stages of the pipeline, but at the same time, right? It is just like that example of like washer dryer, which I mentioned last time. Like you have one bucket in the drying stage, and first bucket in the drying stage, and the second bucket in the washing stage, right? So maybe like I have instruction 1 here, instruction 2 in this stage, instruction 3 in this stage, 4 here, instruction 5 here. But then I don't want the instruction which is fetched to affect the decoding of the next instruction, right? Which means that this instruction should enter into the decode stage only when instruction 4 has entered into the issue stage, right? So what I do is that in between them, I put the buffers. And the job of buffer is like it stores your data signal, data signal, and then the signal is propagated into the subsequent stage only when a clock signal arrives. Okay. So, but then there are like disadvantage, like downsides, not disadvantage, downside of these buffers as well. For example, the more number of pipeline stages you have, the more buffers you will need, and each of them have its own power consumption. So one thing will be the power consumption. Other thing is like it takes time input to appear on the output. It doesn't happen at zero time. So definitely it will introduce latency, right? So ideally we say that, okay, as more and more number of stages we have, the higher performance we will get. But practically when you start increasing the number of stages after a certain point, you start seeing that our head becomes more and more prominent instead of the performance itself. Any questions? No? Okay. Okay. So I'm explaining all these because all these things are mentioned in the paper. And before we go to like the main core contribution of the paper, you need to know these things. So what is read after write hazard? Anyone who knows already? So let's say you have two instructions that I'm saying add R3, R1, R2, and then I say multiply R3, R4, R5. So add is like, and let's say this is the instruction sequence. Okay, my program is progressing in this direction. So I cannot execute multiply before add until the add is done and its result is ready. Why? Because the result of R3 is used as an input operand to multiply. So which basically means that multiply instruction cannot read the value of the register R3 until the R3 register is written by add instruction. So I can read it only after it is written. So I can read after while. So this is like the real dependency which we cannot resolve. So we have to respect it. So when we are like scheduling the instructions, or let's say when we are issuing the instructions, so we need to check if there is a raw dependency or not. So if there is a raw dependency, so then what will happen is that I cannot issue both of them in the same cycle, right? Okay, how this raw hazard hinders the issuance of two consecutive instructions, I think I have explained already, right? So I must first issue this one, and once the result is ready, then I can issue the multiply, okay? I mean, yes, we can forward the data, but let's say we keep the thing simple. We say that, okay, we will issue only when the data result is available in R3, and then we can do the multiplication, okay? Okay, NOP instructions. How many of you, NOP stands for no operation. So if it is doing no operation, then why even we need it? Like it is doing nothing, right? So why we even need it? So sometimes we need to do no operation because we need to flush the pipeline. For example, let's say you have this if else construct, right? And here you have some set of instruction or block of code, and here you have condition, right? And let's say your CPU or your whatever platform you are using has a predictor, branch predictor. And you predict that the condition will be false. So definitely this condition will be first tested, right? But we don't want it to be like its result become available and keep waiting for that. So what we do is we do prediction, and let's say our prediction says that the condition will be false. So we start executing at this point. So, but by the time, so what happens, let's say you have instructions 1, 2, 3, and so on. So what happens is that you start filling your pipeline with these instructions, right? That you will start first fetching the instruction 1, then 2, then 3, and so on. Let's say we are doing single fetch. So your pipeline starts getting filled. But by the time later on what happens that you check the actual result of the condition and it turns out to be misprediction. The branch was taken, right? So which means that you had to execute this part, not this one. So what you need to do is, but your instructions from this block of code, they have entered the pipeline. So you have to flush them, right? So for flushing, what you will do is that you will issue the NOP. So like if you have, let's say 4-stage pipeline, you need 4 NOP instructions to flush everything, like instructions which are partially executed and they have their footprint or their results, partial results in the pipeline. So that's why we need NOP, okay? Okay, barrel shifter. How many of you know the shift operation? So
So if it is a partial instruction, will it not go to the next stage? Will it just be stuck in there? That's why we need the NOP.
sorry, say it again. If it is a partial what?
If it is a partial instruction, does it not go to the next stage at all and is stuck within the buffer? And that's the reason we need the NOP.
No. Just don't get stuck in. They are in the let's say you have when you say stuck in the buffer, it basically means that instruction is occupying this particular stage. Stuck in the buffer means that its data and signals are stored here and they are affecting the combinational logic in this particular stage, right? Executed by this combinational logic or logic layer you have. So it's mean that I want to clear this buffer. So how can I clear if I put all zeros here, right? And NOP does what? It puts all zeros.
So by applying the NOP, you're basically just clearing out the stage.
Yeah.
So the buffer and the stage are with each other, coinciding.
Buffer and stage, you can consider them like almost same thing in the sense that you need a buffer before every stage. So whatever the content you have inside the buffer, it affects whatever is going on in the logic of that stage.
Okay.
So if you have put 0, it's mean everything is resetting to 0. Yes.
I want to perform the knob operation for instruction 2.
This one?
For the buffer, which is at instruction 2. So it should go through all the instructions.
So you will have like how many knobs you need? 1, 2, 3, 4, at least this one.
So let's assume I have to perform the knob operation at 10th instruction. So that many.
You mean 10th stage
Yeah.
of the,
So
yes.
that many knob operations I have to.
If you need to flush all of them, yes. Okay, shift operation. I'm going fast because I don't want to like consume all my time just explaining the background, and then we will have no time to focus on the main contribution of the paper. So it will be like, not very fruitful. So shift operation is like, let's say you have, I'll give you an example of 4-bit register. Let's say you have a 4-bit register and it has the value 0, 1, 1, that's 0, 1, okay. And let's say like there are different variants of the shift operation, like you can have left shift, right shift, arithmetic shifts, and logical shift, and then there is also rotate. I'm not going to explain all of them, but the basic operation is similar. You can go and check what is the difference between them. So let's say I want to do the left shift operation by an amount of 1. So which basically means that if I do this operation, after the operation, the new content of the register will be like, this will be thrown out because I'm doing logical. When you do the arithmetic, it is a bit different, but I'm doing the logical shift operation. So this will be thrown out and everything will be shifted by 1 position towards left. And the least significant bit, it will be filled with 0. And this is most significant bit, okay? And now if I want to shift by 2 positions, then I need to again perform another operation. So what will happen is like, and next time, if I do the shift operation again, so I will have 1, 0, 0, 0. Okay, so I consume 1 cycle here and another cycle here, right? Now consider that my register is not 4-bit. My register is 64-bit, okay? And I want to shift the data by 8 positions towards left, or 16 position by. So how many cycles it will take? 8 cycles or 16 cycles, depending upon the amount of shift you want to perform, which becomes expensive, right? So if it becomes expensive, then is there a way that I can do the shift operation by 16 times, but only in a single cycle? So barrel shifter is the answer to this question. So barrel shifter does that by making some changes in the architecture where you can basically, then it enables you to do 16 shift operation in 1 single cycle. Okay. I'm going to skip it because I have already recorded the video and put it in the canvas. Go and watch it, how barrel shifter does that. Okay. Because then I first need to explain the multiplexer, then how multiplexer is used, and it will take time. Okay. 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 So let me now shift to today's slides. Okay. So yeah, how we can deduce information about number of stages of a pipeline and pipeline of a functional unit by running the micro benchmark. By the way, have you submitted your reading notes? Okay.
Option for the annotated.
No, you have to submit your annotated
There
file.
wasn't something, but it. Should
You
we-
change that? Okay, so she has made the changes, so now you should be able to submit. But even like, okay, don't worry about it. Don't worry about it now. Don't waste the time. If you cannot submit, you can send me the by email, you can send me the annotated file, okay? So let's not waste the time. So how can I get information about number of stages of a pipeline of a functional unit, pipeline functional unit, by running micro benchmark? So let's say you have a multiplier and you have pipelined it. So it has multiple stages, like let's say stage 1, okay, 2, 3, and 4, right? And you issue a multiply instruction. So first instruction, and let's say I'm making it simple, like each stage takes only 1 cycle, okay? So it's mean your first instruction, multiply instruction, will become ready after 4 cycles, right? You will get the output after 4 cycles because it need to pass through all the stages. So this is like latency of your single instruction. But that is the case when you only for the first multiply instruction. But after that, if you keep feeding subsequent multiply instructions, what will happen that after 4 cycles, your pipeline will become full, right? You will have multiply 1 here, multiply 2 here, 3 here, and 4 here. Now, after that, what will happen that after every cycle, you will get the output of 1 multiply instruction, right? So because in next cycle, this will be output, you will get the output of this one. And in the next cycle, M2 will move here, everything will move to the right. So for every subsequent instruction, you will start getting the result of multiply instruction ready, right? So it's mean that once your pipeline is full, you have a sustained CPI of 1. So CPI, what is CPI?
Per instruction,
Sorry?
cycles per instruction?
Yeah. So how long it takes for one cycle, how many cycles it take to execute an instruction, okay? So if you have once you have filled the pipeline, and then after that, you will have 1 instruction available on the output, right? So based on that, so this gives me the information for the first instruction. It gives me okay, how many cycles it takes to complete the multiplication. So if it takes let's say the 4 cycles, and every stage I'm assuming is taking 1 cycle, it's mean that in total there are 4 stages, right? Okay, so let's go here. Now, this is one of the main contribution of the paper. So as I said at the start, at the time when they were writing the paper, there were no detail was available about the ARM Cortex A7 processor. The only logical diagram or logical information wasn't there. So they want to ask these questions, they want to answer these questions, that in this CPU, how many ALUs are present? And can they all compute all the functions? All the functions mean if you have an ALU, can it do addition? Can it do logical operation? Can it do multiplication? And so forth, right? Or maybe it is possible, is it the case that only one ALU can do the multiplication and the other cannot? Okay. Second, are units performing multi-cycle instructions, for example, multiply, shift, LDR, SCR, etc., are pipelined or not? So they know that the multiply instruction, for example, take multiple cycles, but whether the multiplier itself is pipelined or not. And third, they wanted to get the information about how many data buses connect the pipeline stages. Like for example, let's say from fetch to decode and decode to issue, how many data line, the data bus which is crossing, what is the number of data buses crossing the stage, okay? So the question was how can we infer this information by performing CPI indexing of different instruction benchmarks? CPI indexing is what you do is definitely you will run a benchmark, and then you will record, you will run it multiple times, and then you will average that how many cycles are consumed per instruction to execute that benchmark. Okay. So anyone who would like to answer that, how I can actually it is shown here. So it says CPI is, if CPI is equal to 0.5, then they are deducing that we can perform the dual issue between ALU with immediate operand and another ALU instruction, we can do the dual issue between an ALU instruction with immediate operand and another ALU instruction with immediate operand. Yeah.
So, I guess from my understanding, the idea is we're loading this buffer that you're talking about earlier with all these instructions, and then they're measuring, so once it's full, then they're just running a bunch of tests to measure how many clocks it's taking and putting it into this table.
Yeah. So like they like you have a benchmark, let's say you have add R1, R2, R3. And you have another, in this benchmark, you have another instruction, which is like, let's say R4, R2, R5, and R6. So when they run this benchmark, they find out that CPI is not 0.5, it is 1, right? So which means that if CPI is 1, then it's mean that every instruction, both of these are taking 1 cycle. So if both of them are taking 1 cycle, it's mean they both of them are not issued in the same cycle, right? So, but they observe that if they have another benchmark, let's say R3, R2, and R1, and the second instruction in this benchmark is an immediate number, a register 4 and 5. Then they found like if they run this benchmark like multiple times and measure its CPI, they found that it gets completed in 0.5 clock per instruction, which basically means that both of these instructions are issued in the same cycle. So from this, they deduce that, okay, if there are 2 ALU instructions and both of them have no immediate operand, they cannot be issued in the same cycle. But if there are 2 ALU instructions and one of them has an immediate operand, they can be issued like this case. They can be issued in the same cycle. So the dual issue is, the processor is doing dual issue. So the one question that they wanted to answer was like, yes, you said partially dual issue. What does it mean by partially dual issue? So here, this is what meant that, okay, in this case, I can do the dual issue, but then in this case, I cannot. Like ALU and ALU, both are ALU instruction, I cannot do the dual issue. Okay, yes, sorry.
I think I have one question I have while reading is when they're calculating how many ALUs are present, how it correlates to the CPI. Like if there was 4 ALUs, would it be 0.25? The CPI?
How many ALUs are present?
Yeah, or like the correlation between CPI and.
Okay, anyone who want to answer that how many ALUs are present? So, okay, this gives us information about the dual issue, but how can we deduce the information about the number of the ALU present?
What one?
Actually, it is also, you can deduce the same information also from here. Because you get the CPI when your instruction is completed, its execution is completed, right? So if its execution has completed, it means it has passed through the execution stage. So if it has passed through the execution stage, it's mean both of them have been executed, right? That's why you are getting the CPI of 0.5. So if both of them have been executed, then it's mean you need 2 ALUs at least. Like, I mean, if it is like 0.25, then you will have 4, right? So that is how you get the information on that. They deduce the information about that.
What is the IMM?
Immediate number. IMM immediate. So it stands for immediate. So okay, I don't know. I need to explain like too much background. So here is what happened is like when you do the ALU instructions, like in some cases, remember I talked about the ISA. So ISA, it not only gives you the list of the instructions that need to be executed on a processor implementing that ISA, but it also gives you details about addressing modes. Like for example, I'm doing here add instruction. So, okay, here I'm specifying that, okay, there are 2 source operands, but where are those source operands located? Here I'm saying one of them is in R1 register, another is in R2, right? But I cannot, here I'm saying that, yes, there are 2 source operands. One of them is located in R4, and another is the part of the instruction code itself. So instructions, they're like everything is in binary form, right? So instructions are also in the binary form. So your instruction has like a template, and then based on that template and the opcode. I don't want to explain what is opcode, but based on the template, you can actually detect that, okay, whether this particular instruction needs the will read the source code from the register, or it is the part of the instruction itself. So if it is part of the instruction itself, we name it as immediate operand. So you don't need to read it from the register file. It is embedded in the instruction code itself.
So like just put in a number like take.
Yeah. So like immediate number is like, let's say it can be like 6 or 10 or something. Okay. Any other thing? Any other question?
So in conclusion, there's only two ALUs, one for the registers and the other one that functions with immediate numbers.
No, we are not saying that there are two ALUs, one for the registers. And what we are saying is that there are two ALU, but what this information, what this table is telling us, that we can have one ALU instruction with immediate number, dual issue either with another ALU which doesn't have the immediate number or immediate operand, and another ALU which has the immediate operand. But it doesn't say that one of those ALU can only perform this ALU instruction and the other can perform only the ALU instruction with immediate number. No, both of them. It doesn't tell us about that thing. Okay.
Okay.
Can a timing attack be done here? So if you figure out that there's like, a cycle for instruction, you can guess the architecture.
If we can guess what?
The architecture based on if you read that it's only the clock cycle for instruction.
Timing attack, by looking at the timing, you are actually deducing the information. This is what you are doing already in CPI, right? So by looking at the timing of different micro benchmarks here, right? You are getting the information. You don't know already what is inside, but by looking at the timing, you are getting the information. And CPI is a form of timing, right? Yeah. Okay. So again, I think it is already answered. We deduce that, oh, no, it's a different question. They are deducing here that there are two ALU present by the fact that you can do the two arithmetic instructions at the same time. I haven't copied everything, but you can do the two ALU operations at the same time only if one of them is the immediate, right? So which tell us something about register file. That's why I think they need a course in computer architecture first. You have the register file here. So you have read ports, right? And you have address, and then you have some signals. But if you are saying that, okay, you can do the two ALU instructions, only one of them is immediate and the other is not. So if one of them is immediate, you are reading one operand from the register. And for the other one, you are reading both of the operands from the register file, right? So which means that you can dual issue it only because you need three data ports, three output ports, right? So you have read port 1, read port 2, read port 3. But you cannot do this one. You cannot do the dual issue for this benchmark because you need to read 4 registers at the same time. So based on this, they are inferring the information that the register file has 3 output ports. Okay. Okay. So the one second part of the first question was like, how many ALUs are present? So they have answered that, and then can all of them compute all the functions or all the operations? So to answer that, they run the different benchmarks, and then they found that multiply instruction or the shift instruction, both, they cannot be issued in the same cycle with an ALU instruction. So which basically means that not both of them, both of the ALU can perform the multiply instructions. This they have not mentioned in the paper, but my understanding is like, since your CPI is equal to 1, when you issue multiply instruction, and if in a benchmark you have multiply and the ALU instruction, so CPI is equal to 1. So it's mean there is no dual issues happening. So only one ALU is equipped with the base shift, with the barrel shifter or the multiplier. So, but they don't know which one of them have the barrel shifter or the multiplier. So my understanding is like, because of that uncertainty that which one of these two LU has the barrel shifter and the multiplier, they have to like issue the ALU instruction and the multiply instruction in separate cycles. I don't know whether you got me or not. So let's say you have two ALUs, right? And you want to issue, you have two instructions to execute, add and multiply, right? So let's say that we don't have any problem in reading from the register file because of the limited ports. Let's say this add is like immediate. And then if I know that, okay, this ALU has the multiplier, I should be able to send it here and send this one here, right? But they are observing that CPI is equal to 1, not 0.5. So which basically means that my understanding is they don't know which one of them have the multiplier available while they are issuing. Okay, any questions?
Thing, it says they are not identical, but if there was ever a situation that they were identical, what would happen to the whole operation?
So if they were identical, then okay, anyone who want to answer her question? She's saying that when she's looking at the paper, they say that they found that the ALUs are not identical. Not identical in the sense that only one of them can perform the multiplier shift operation. The other cannot. Yes, there are two ALUs, but they are different in their capabilities. So her question is like, let's say if they are identical, then what will be the implication, right?
Wouldn't it be acting as like a singular ALU at that point, since they're both doing the same operation?
When you be able to dual issue, like say the multiply, since you can have one multiply on the first LU, the other one.
Then we will be able to do, yes, to dual issue, and we will have a better CPI. Like, for example, let's say 0.5. Because then again, if everything else works, let's say your register file supports it, like you can read multiple, all the operands of two instructions at the same time. Let's say if that is supported, and you have two ALUs, both are identical, both can do the multiplication, you can issue two multiply instructions at the same time, right? But if you go back into this table, so multiply instruction cannot be dual issue with another multiply instruction in this case.
Regarding the comment about the issue stage can't know which LU has a shifter multiplier, doesn't it know that the LU that handles the immediate instruction has the shifter?
No,
that the other one has the shifter, that the LU without.
No,
immediate.
ALU has no, whether you can execute an instruction with immediate number is not related with the capability of ALU. The problem is coming from the register file. Remember? I mean,
Yeah.
you have 3 ports. So that's why you can, for ALU, it doesn't matter from where the data is coming, whether it's coming from the register or it is coming from like immediate part of the instruction itself. It doesn't matter.
Does the shift take a constant and immediate, or it has to be in the register?
That's
Shift.
is on the
In
table.
this architecture, like it's a shift R1, R2, and then an immediate or a register, or it could be both.
They have not shown in the paper, but I think that in the example micro benchmarks, they haven't included the shift instruction with an immediate operand. But I would assume that since they are, I would assume that shift includes the case where you can provide them data in immediate form instead of like register.
So if it's an immediate, then with a multiply, you could have only 3 registers requested.
Yes.
And then, if that's the case, then it would be similar to the case where you could issue the 2, but since it doesn't, this probably means if that's the case, then probably the multiply and the shifter are on the same ALU.
Yes, yes. And this is what exactly they said, that shifter and multiplier are only one ALU, not like both of them. Like only one is equipped with both of them, shifter and multiplier.
So that why you can't necessarily tell if it's one or the other, because they could be technically.
Yeah,
the
my
same.
understanding is that we cannot tell because.
Yeah, I mean, if there is 2 ALUs, there is no way for you to tell which is which.
Yeah.
It's 2 ALUs, one does this, the other doesn't, that's it.
Yeah, but I mean, it should be possible, like, to include that information in the issue stage, which one of them is.
Internally, the architecture
Yeah,
knows, but
yeah.
externally, there is no way for you to
Yeah, I
discern
cannot
that
figure
from
out.
just micro benchmark.
Yeah, from micro benchmarks, yes. Okay. Okay, so coming to the second question, let me check the time. Okay, so coming to the second question, which like in the last list of the questions they had at the start was like, yes, are units performing the multi-cycle instructions, like for example, multiply instructions, shift, load register, store register, all these instructions, the units which are performing these instructions, are they by themselves pipelined or not, right? So they found that their finding is that all of them are pipelined. For example, they observe, let me read. We report that the CPI of a sequence of either load or store instruction, free from data hazards, resulted in a sustained CPI of 1, indicating that the load store unit of the Cortex A7 is fully pipelined. Anyone want to explain this? Actually, I gave you a hint before or earlier, like how you can get this information by looking at CPI. So load store units, they are responsible for handling the load instruction, which actually loads the data from the memory into a register, and store instructions, which pick the data from particular register and put it back in the memory. Now the operation, the procedure that the whole operation is done is like, they are doing it in multiple steps. So since what they did is like this. So let's say you have a benchmark which has a bunch of load instructions, load register, something here. I'm not writing that one. Load register and so on. So when they execute this benchmark, and multiple times and average the result of CPI, they found that the result is 1, which means that every subsequent load instruction gets ready or its execution is complete after every 1 cycle. So if that is the case, then it means that your load store unit is pipelined, right? Otherwise, then the latency of accessing the data from memory, like load instruction or store instruction, it is expensive, it is large. So it can be 1 only if you have already pipelined your load store unit. That's why you can have 1 load operation or a store operation completed in every cycle. Remember, like I gave you example, if you have one adder, which is not pipelined, and it takes 10 cycles, right? So same kind of approach. And they also observed the same thing about the multiplier. So basically what they did is, like, instead of running a sequence of load register instruction, they run a sequence of multiply instruction. And again, they observed the CPI of 1. So they make the same conclusion. Okay. I think I have discussed already this one, like how many databases are there by, yeah. because they were able to, by looking at like, okay, how many ALU instructions I can issue? Yeah, I can issue two of them, but only if one of them is immediate. So it's mean that there are three register outputs crossing from the decode stage into the issue stage, and one bus which has the immediate number going into the subsequent stage, right? And on top of that, because they are able to complete, how to say, 2 ALU instructions in one cycle. So ALU instructions, they write back, those which write back into the register, let's say here, right? So if you are able to complete these two in a single cycle, it means you are able to write both R3 and R5 in the register file at the same time. So it's mean you have two input data lines, right? Coming back from the last stage here into the register file. So register file is, I'm assuming, is it in the decode stage. So after their investigation, like after doing the CPI indexing for different kind of micro benchmarks and looking at the results, they constructed a figure describing what they think about the internal details of the ARM Cortex processor. So like they find out that, okay, in the register file, you have 3 output ports, you have 2 output ports. They found out that you have multiple ALUs, and then they find out that one of them has single stage, the other is 3 stages, and load stage, store unit, and FPU, they are also pipelined. So then definitely they are putting the multiplexer, because the result which is sent to the next stage, it depends upon which kind of instruction you are executing, right? So if you are executing the, let's say, some load store instruction, the result needs to go from this input. And if you are doing ALU instruction, the result need to go from this input. Multiplexer, for those of you who don't know, multiplexer is a component which can actually, what it can do is like, if you have, let's say you have port cross 1 multiplexer. So it has 4 inputs. And what it does is, and 1 output, and depending upon control signals, it will select one of these input and connect it to the output. Okay. Any questions? Okay, so they have inferred this information. So definitely one thing is like, just by doing the CPI profiling or CPI indexing, they were able to find the information which was not openly available, right? So how is this information useful for an adversary? Maybe at that time, not now. So let's say the Cortex A7 was like state-of-the-art processor at that time, and if you can get this information about the architectural detail and all the architectural details about the CPU, maybe you can say, okay, I can now devise a better chip than this one by doing my own optimizations. And this is like kind of your information leakage. Okay, so if you have like read the paper in how to say, in a structured way, you may have found that there are 2 main contributions. One is like they use the CPI indexing to figure out the hidden architectural details of the processor. And second, they do the power analysis to find out the sources of information leakage, architectural sources of information leakage. And in doing that, what they are doing is like, they are not only doing the power analysis, what they are saying is like, the power profile they found, it reflects the Hamming distance and Hamming weights of the different value of the values stored in different registers or different architectural components of the processor along the at different times along the execution of the instructions or micro benchmarks. So what is Hamming weight of a number? So it is like how many, if when you convert it into the binary form, how many of the bits they are non-zero or one number of ones bit. So that is the Hamming weight. And Hamming distance is like if you have two numbers both represented in binary form, so how many bit positions they differ in their value. Okay, clear?
There is one thing I was noticing on the paper is that they did a lot of stuff, including one of these Hamming things, where they would just like mention these terminologies that I technically hadn't really heard beforehand, but wouldn't ever like go into detail on it. Is that just because they assumed people reading it would be familiar with those terms
Yeah.
already?
So research papers are definitely written by researchers and then most of the time read by researchers. So this is like this kind of information they will they have not explained what is Hamming distance or what is Hamming weight or what is a pipeline buffer, right? Why? Because it is considered a common knowledge. So the expectation is that everyone who is reading the paper is aware of all these things. But that is not the case in our class because one, most of you are undergrad students. Second, I don't think you have taken any architecture course, right? So, I mean, that's why I need to like explain all of these things. Like, otherwise, like if you had all this knowledge already, then reading the paper and understanding it will be relatively much easier, right? Okay, so your question?
Question of the Hamming distance, was that the one next to the line here? Because in the paper, it says like, only the Hamming, so I'm gonna quote it, because only Hamming distances between operands in the same source operand position show significant leakages since they share the same bus. My question is, how do they share the same bus?
Oh, okay, I will come back to that. But let me explain the things in order because if I directly go to that, what you are saying first, I will not be able to explain and most of you will not be able to understand. Okay, so everyone knows what is Hamming weight and Hamming distance. So we have 4 minutes, right? Okay, so for the second part of the paper, they are definitely using Hamming weight as a tool and Hamming distance as a tool, but besides that, they are also doing the power analysis. So what is power analysis and how power analysis can reveal the information? So just to give an example, like, okay, the bottom line is that every operation you do in, is it fine if I write here? Yeah. So the bottom line is that every operation you do in the CPU, it is at the device level, it is done by transistors, right? So the data which you store is stored in like elements which are made of transistors. When you change those, let's say you have this transistor, I'm like just drawing the block diagram and it stores the value. Let's say this is your memory cell, okay? So this memory cell itself is consisted of multiple transistors. I'm not going there, right? But let's say it stores the value currently of 1 and I want to change it. So if I want to change it and let's say I want to set it to 0, right? So then it's mean that I will give some input and as a result of that input, some electrical current will flow through the transistors. As a result of that flow of the electrical current and the power will be consumed, right? Now, if I am like frequently switching it from like 1 to 0, 0 to 1, then 1 to 0, then 0 to 1, I'm consuming more power, right? So now, let's say you have a number 1 0 1 0 1 0 1 0. Let's say this is A, and I have B, right? And I do the operation 1 0. I do the and I have 1 1 1 1 1 1, right? And I store the result in C. And the operation I'm doing is exclusive OR. Let me say, let me keep it simple. Or all of you know how OR works, right? So if I do R, what will be the result?
All ones.
R1. I'm not writing, right? Now let's say I'm changing the B. And if I change the B, and let's say the previous result before doing the operation was R1. And then I do this operation and the content of C doesn't change. It will still be R1, all ones, right? Now if I change the B, which is my input operand, and I change its value, and I change its value to 0, 0, 0, 0, 0, 0, 0, 0. So what will be the result here? A. So 0, 1, 0, 1, 0, 1, 0, 1. How many of them change their state as compared to the previous was 1, 1, 1, 1, 1, 1, 1. This changed the state, this changed the state, this changed the state, this changed the state. 4 of them changed the state, which means they were discharged, the transistors were discharged. So when they discharge, they consume power, right? So now 4 of them are discharged, and power equal to discharging of 4 transistors, to make it very simple, is consumed, right? But if I change my operand such that all of them are set to 0, previously all of them 1, and now all of them are set to 0, right? So all of them are discharged, more power is consumed, right? Now by looking at the power which is consumed, by recording that power and looking at its trace, I can get information what is happening in the C, right? Which give me some information about what is the value of A and B. If I know the operation, and I know the operation, how I can know the operation? By issuing an instruction R, C, A, B. I can control this, I can control this, I can look at the power consumption of this, right? So I'm not going through this, but the main idea is that when you look at the power consumption profile of a processor, it can potentially reveal the information, not only what kind of data is being processed, but also what kind of operation is being executed. Let's say you have the same data, but remember here I changed the data, but instead operation was same. Or you can also have the same data, but change the operation, and still the output will change, which means the power consumption will also change, right? So this gives you details about, like, the thing is, like, depending upon the data or depending upon the operation, the power consumption will be different. So then you can do the mapping, right? Like, okay, when this operation is performed, then I observe this kind of power consumption pattern or profile. And when I do this kind of operation, then I see a different type of power consumption profile. I must stop here because we are running short of time. But go through the slide or complete reading your papers if you haven't completed it already. And if you have questions, you can visit me in office hours. I won't prefer emails. You can send emails, but then emails are not suitable for having fruitful discussion, right? So if you have questions, visit me in office hours.